In this video, we're going to talk about performance optimization. We'll compare a for loop and a vectorized operation to see which performs better. Both approaches have their uses, but we'll see that vectorized operations are generally much faster. I'll explain this more in the next section when we discuss time complexity. Let's walk through the code quickly. We first build an array with a size of about 1 million elements. Then we generate two random arrays, each with a size of 1 million. Here's the loop version we add arrays. And a b element by element inside a for loop. We also measure the time it takes by recording the start time and end time, then taking the difference between them. These zeros array here is simply used to initialize an empty NumPy array as a placeholder. Each time the loop runs, it stores the result in this NumPy zeros array. Next, we look at the vectorized operation. You can immediately see that the code is much simpler and cleaner. Instead of looping through each element, we just use e plus b, and NumPy handles all the element-wise operations internally. We time this in the same way by recording the start and end times and then calculating the duration. When we print the results, you can see that the for loop execution takes about 0.516495 seconds, while the vectorized operation takes only about 0.006 seconds. That's roughly 80 to 83 times faster. This clearly shows the advantage of using NumPy for numerical computations. It's not just cleaner, it's significantly quicker for large-scale operations. Now, let's briefly talk about time complexity, which is useful to understand in programming. In our case, both the NumPy vectorized operation and the for loop are of order O of n, meaning their execution time increases linearly with the number of elements. However, as we saw, NumPy's internal implementation is far more efficient. Here's a general idea of different levels of time complexity. It starts with constant time, O of 1, which is the most efficient. Then comes logarithmic time, O of log n, which is also very efficient. Linear time, O of n, is still efficient and scales well, which is what we observed in our example. Beyond that, we have polynomial time complexities like O of n squared and O of n cubed, which get slower as the data size increases. We'll later visualize these complexities in a graph using code so you can see how execution time worsens as complexity grows. Understanding this helps you gauge how efficiently your program runs. Naturally, the faster, the better. That's it for now. In the next section, we'll be talking about linear algebra.